Let us solve some more questions on structural isomerism. In this, two are subjective questions and remaining all are objective questions. You will have options. So in the first question, write the number of structures possible with C7H8O which contain at least one phenyl group. So the same pattern I am following. First I am going to find a degree of unsaturation, number of carbon atoms plus 1 minus number of hydrogen atoms by 2. No halogen, no nitrogen. So the degree of unsaturation is 4, and he is saying every structure should have phenyl group. If you can recollect, in case of a phenyl group, degree of unsaturation is 4. So 3 pi bonds and 1 ring. And also you have oxygen. Whenever you have oxygen, one oxygen, the possible structures are aldehydes, ketones, alcohols, ethers. But if you are trying to write aldehyde functional group itself has one degree of unsaturation. The molecule has a degree of unsaturation 4. Already in the form of a phenyl group, you are covering the degree of unsaturation 4. So it can't be aldehyde, because if you write aldehyde on benzene ring, total molecule degree of unsaturation becomes 5, but the given degree of unsaturation is 4. So it must be alcohol, ether. So first let us write alcohol structures. So we have benzene ring. This is carbon skeleton we are writing. You can write a OH group here. Otherwise, this is carbon skeleton. Methyl benzene, that is toluene, we can say OH group at ortho position, OH group at meta position, OH group at a para position. So these are the 4 alcohols possible. Next, ethers are also possible. In case of ethers, this is the only possible structure, methoxybenzene. It is also known as anisole. So this is aliphatic alcohol, aromatic alcohol, aromatic alcohol, aromatic alcohol. This is ether. So totally, in case of this, in fact, this is called aliphatic alcohols, and these are phenols, and this is ether. So totally 5 isomers are possible. So this is about C7H8O. Now in the next question, write the possible structures for the molecule having the formula C8H10O, which contains at least one phenyl group. First let us find degree of unsaturation. Degree of unsaturation is number of carbon atoms plus 1 minus number of hydrogen atoms by 2. So degree of unsaturation is again 4, and the condition imposed is there must be one benzene ring, there must be one phenyl group in every structure. Phenyl group degree of unsaturation is 4. That means whatever the degree of unsaturation possessed by the molecule is in the form of benzene ring. There is also one oxygen. If you are trying to write aldehyde ketone in the side chain, the total degree of unsaturation of the molecule becomes 5. So aldehydes, ketones are not possible, only alcohols and ethers. So let us take the skeleton first. So here this is benzene ring. Totally there are 8 carbon atoms. I am taking ethyl group like this. Two methyl groups like this. Two methyl groups like this. Meta position, para position. Now from this, what are the possible alcohols? You can write OH group here, here, result is different. You can write here, here, here. Like this, I'm going to write OH group structures, alcohols and phenols from this. Like this, here one structure, here OH group, with respect to ethyl group at ortho position, at meta position, and at para position, like this, from this. Now, when you take orthoxylene, you write OH here or here, the result is same, because both this one and this one are identical. You write OH group here or here, the result is same, because if you write OH group here, that is next to methyl group carbon. Even if you write OH here, that is same. You write OH here or here, the result is same. So all possibilities. So what is meant by same result? You just write the structure and check. Here I am writing OH group, one possibility. Here I am writing OH group, one possibility. Aromatic alcohol, this is a different possibility. Even if you write here, the result will be same. You remove this OH and write here, the result will be same. So these are the three structures possible from orthoxylene. Now metaxylene. In case of metaxylene, what are the possibilities? Let us discuss. You write here or here, the result is same. You write here or here, the result is same. And here the result is different. Of course, here also the result is different. So I am writing OH here, OH here, OH next to methyl carbon, like this. These are the possibilities from metaxylene. And in case of paraxylene, you write here or here, the result is same. You write here or here or here or here, the result is the same. If you want, you write the structure and try to give the IUPAC name, you will end up with the same IUPAC name. So this is OH I am taking, and here I am writing OH here. If you are worrying about another position, one example let me write. Here what happened will, here what happened, if you observe, OH containing carbon will be the first carbon, second carbon, and this is the fifth carbon. First carbon, second carbon, fifth carbon. If you try to give the IUPAC name, these two will get the same IUPAC name. They are identical. They are definitely identical. Now we can also write ethers. These are all alcohols and phenols. We can also write ethers. Alcohols and phenols we wrote so far. We can write ethers also. So carbon skeleton, let me take again. This is ethyl benzene. Dimethyl benzenes also. We are writing ethers. Oxygen should be present between two alkyl groups. You can insert oxygen here. As a result, it will become like this. This is the compound. From dimethyl benzene derivatives, this is one possibility. We can change the position, meta position. Now we can write at a para position. So these are the different isomers possible for this molecular formula. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. But in exam generally they impose conditions, accordingly you can write. Now let us solve some objective questions. In the next question, how many different terminal alkynes are possible for the compound having the molecular formula C6H10? He is asking terminal alkynes. 0 is not there, the answer. So obviously it has to have degree of unsaturation 2, but still let us first count degree of unsaturation. So that is 6 plus 1 minus 10 by 2. So here that is 7 minus 5, degree of unsaturation is 2. But he is asking terminal alkynes. He is asking terminal alkynes. So totally there are 6 carbon atoms. So this is 3, 4, 5, 6 carbon atoms. In this 6 carbon chain, we have to write only terminal alkynes. This is one possibility. Now we have to take a 5 carbon chain. Terminal alkynes he is asking. You can write a methyl group here. Again 5 carbon chain I am taking. You can write methyl group here. So this is a 5 carbon chain. Let us try for 4 carbon chain like this. And here we have totally 6 carbon atoms. You can write 2 methyl groups like this. And if you try to write ethyl group, what will happen? You see that becomes 5 carbon chain. 1, 2, 3, 4, 5. 5 carbon chain. Already 5 carbon chains we have drawn. Therefore, that is not isomer, that is identical. So 4 carbon chain. And 3 carbon chain, if you are trying to write, definitely it is not possible, because you have to put some branches here only, but already tetravalency of carbon is satisfied, so 3 carbon chain is not possible. So here the answer, this is 1, 2, 3, 4. So the answer must be 4. Yes, the given answer is also B, so that is 4. In the next question, there are 8 isomers that have the molecular formula C5H11Br. Among these, how many are tertiary alkyl bromides? He is not asking to write all 8 isomers, but he is saying in those 8 isomers, how many are tertiary? Simply let us write a tertiary alkyl halides, tertiary alkyl bromides. Totally there are 5 carbon atoms. If you take 5 carbon chain like this, tertiary is not possible. So this is not giving tertiary. Let us take a 4 carbon chain. Here tertiary is possible. Next let us take a 3 carbon chain. So totally there are 5 carbons. If you are trying to write a bromines on this, you will not get a tertiary. If you are writing bromines, if you write bromine here, that is not tertiary. Here it is not tertiary. Here it is a secondary. Here it is a primary. Only from this it is possible. Even from this, there is no tertiary carbon. In fact, here it is primary. Here it is quaternary, but tetravalence is already satisfied. So from this also it is not possible. So only one tertiary bromide is possible. So the answer must be B. Given answer is B. Let us move on to the next question. Here the question says, how many positional isomers are possible for this structure they are asking. How many positional isomers, and they are asking only cyclic isomers. The given compound has one ring, therefore degree of unsaturation is 1. Totally there are 6 carbon atoms, 1 nitrogen atom. Degree of unsaturation is 1. First let us write all possible isomers. First I am writing a 6 membered ring. 6 membered ring with NH2 group. Next one, 5 membered ring. Given structure I am writing. Given structure, so that is a CH2 NH2. Now I'm writing another possibility, another structure. I'm going to interchange the position of this NH2 group and this hydrogen. As a result, I will get CH3 NH2, NH2 and CH3 on same carbon, CH3 and NH2 on adjacent carbons, 1 and 2 carbons. Even I can write one more possibility, that is CH3 and NH2. For example, even if you write here by removing this, that will be same. If you write here, then this is first carbon, second carbon, third carbon, 1 3 position. Here also the same thing, first carbon, third carbon. So these are the different structures possible. But most importantly in this is the first one, let me write, this is the second one, third one, fourth one and fifth one. If you carefully observe, in case of the first one, here it is a 6-membered ring. Principal carbon chain is this one because NH2 is attached to ring system. But here principal carbon chain has only one carbon because NH2 is attached to this. So these two are definitely chain isomers. In this second one, just now I told you NH2 is attached to this carbon. This is the principal carbon chain. There is only one carbon. Principal carbon chain has only one carbon. But here, principal carbon chain, it is a 5 carbon chain. It is also 5 carbon chain. Even this is also 5 carbon chain. That means if you take second one and third one, definitely they are chain isomers. But if the question is like how many positional isomers are possible for this compound, if they say, if their intention is that one, answer must be 0. But in the options 0 is not there. Therefore we need to understand the question like, for this structure, for this formula, how many positional isomers are possible. So if you take third one, fourth one, fifth one, these are positional isomers because NH2 carbon, NH2 containing carbon is first carbon. So this is methyl group at first place, methyl group at second place, methyl group at third place. So 3, 4, 5 are positional isomers. Since 0 is not there, I'm going for a 3, when 3 isomers. That means option A is the answer. Yes, given answer also you can see that is A. Totally 3 isomers are possible. What are the 3 means? These are the 3. Most importantly, the given structure and these are chain isomers. Now let us take the next question. How many structural isomers are possible for C8H16 that have a 6-membered ring? So we have to write only the isomers having 6-membered ring. 6-membered ring structure here writing means degree of unsaturation of the ring is 1. First given formula is C8H16. If you find degree of unsaturation, number of carbon atoms plus 1 minus 16 by 2, degree of unsaturation is 1, and you have to satisfy that degree of unsaturation in the form of ring. Therefore there is no double bond in the ring. But here the condition imposed was only 6-membered rings. We have to write only 6-membered rings like this. Totally there are 8 carbons. 6 carbons are written in the form of ring. So remaining 2 carbons we can write ethyl group, or we can write 2 methyl groups. 2 methyl groups, however it may be. First let me write ethyl group like this. After that I am writing methyl groups, 2 methyl groups on same carbon, 2 methyl groups on 1 2 carbons, 2 methyl groups on 1 3 carbons, 2 methyl groups on 1 4 carbons. So here the structural isomers possible for the formula C8H16 that have 6-membered ring. So 1 2 3 4 5. So answer must be 5. That 5 is given in option B. So the answer must be B. You can see the answer given is B. So that is 5. In the next question, How many structural isomers are possible for molecular formula C3H6BrCl? How to proceed? You see, C3H6BrCl, degree of unsaturation, number of carbon atoms plus 1 minus number of hydrogen atoms plus number of halogen atoms by 2. So degree of unsaturation is 0. If you write all isomers systematically, you will get the correct answer. Otherwise, if you miss one isomer, obviously instead of 6 you may get 5, instead of 7 you may get 6. You should be very careful and you should proceed systematically. And the degree of unsaturation is 0. There are 3 carbon atoms. Bromine and chlorine I am taking on same carbon. Bromine and chlorine on same carbon. Even if you write bromine and chlorine here, that will be similar to this. So this position is a geminal position. Both are on same carbon. Now let us take bromine and chlorine on adjacent carbon, and here immediately chlorine at first place, bromine at second place. Even one more possibility, bromine and chlorine at 1 and 3 positions. So if you write systematically, you will not miss even a single isomer. Bromine chlorine on same carbon, first carbon. Bromine chlorine again on same carbon, that is second carbon. Bromine and chlorine are on adjacent carbons, 1 and 2. Here 1 bromo, 2 chloro, but here 2 bromo, 1 chloro. That is also possible. Bromine and chlorine are at a 1 and 3 position. Totally, you will get only 5 structural isomers. So the answer given is B. In the next question, how many structural isomers of C6H12 may contain 4-membered ring? C6H12 4-membered ring. Cyclic structure, that is butane structure, cyclobutane structures he is asking. So let us proceed systematically. Degree of unsaturation, number of carbon atoms plus 1 minus number of hydrogen atoms by 2. Degree of unsaturation is 1. And you are supposed to write cyclobutane ring structures. That means whatever the degree of unsaturation possessed by the molecule, you are writing in the form of ring. Therefore, in the side chain or in the ring system, there is no pi bond. Most importantly, here 4 carbon chains, 4-membered rings we are writing. Totally there are 6 carbon atoms. 4 carbon atoms are written in the form of ring. Remaining 2 carbons, these remaining 2 carbons can be in the form of ethyl group or 2 methyl groups. Both are possible. So ethyl group I am taking like this. There is no other possibility with cyclobutane and ethyl group. 2 methyl groups on same carbon, 2 methyl groups on adjacent carbons, 2 methyl groups on alternate carbons. Even if you write like this by removing this, that is the same. So this is ethyl cyclobutane, 1,1 dimethyl cyclobutane, 1,2 dimethyl cyclobutane, 1,3 dimethyl cyclobutane. These two are chain isomers, but these are positional isomers. But whatever we are getting with the given conditions, we are getting 4 isomers, and answer must be B. So the given answer is B. 4 isomers are possible with that condition. The next question, how many structural isomers of C6H12 may contain 3-membered ring? Molecular formula is the same as the previous question, but still let us do. Degree of unsaturation 6 plus 1 minus 12 by 2, degree of unsaturation is 1. But the condition is we have to write a 3-membered rings. 3-membered rings. 3 carbons are already covered. Totally there are 6 carbon atoms, 3 carbons are forming ring structure, remaining 3 carbons In case of remaining 3 carbons, what are the possibilities if you take? See, systematically I am solving. 3 carbons can be present in the form of a propyl group, otherwise ethyl and methyl are 3 methyl groups. 3 methyl groups. Whenever you are writing propyl group, one is n-propyl, another one is isopropyl. If you write all these possibilities like this, you will not miss even a single isomer. Let us write all possibilities. First I am writing n-propyl group, immediately isopropyl group. This combination is over. Next, ethyl group, methyl group on same carbon, ethyl group, methyl group on adjacent carbons. Next possibility, 3 methyl groups, 2 methyl groups on one carbon, 1 methyl group on adjacent carbon, or 3 methyl groups on 3 adjacent carbons like this. Here this is 1 comma 1 comma 2 trimethyl, this is 1 comma 2 comma 3 trimethyl, this is 1 ethyl 2 methyl, this is 1 ethyl 1 methyl, this is isopropyl cyclopropane, this is n-propyl cyclopropane. But here when we do it systematically, we are getting 1 2 3 4 5 6, totally 6 isomers we are getting. So the answer must be 6. So the given answer is C. So that is 6 isomers. See, systematically if you proceed, you will get the correct answer. In the next question, how many structural isomers of C9H18 may have 6-membered ring and are tri-substituted? See, two conditions he imposed. Let us follow the same procedure, but quickly. Degree of unsaturation, number of carbon atoms plus 1 minus hydrogen atoms by 2. So degree of unsaturation is 1. You have to write a 6-membered ring. Degree of unsaturation is already maintained in the form of ring. Therefore, there is no pi bond. Totally, there are 9 carbon atoms. 6 carbon atoms are drawn in the form of ring. Remaining 3 carbon atoms, actual possibilities, propyl group, ethyl and methyl, 3 methyl groups. But here, according to the given condition, tri-substituted. Tri-substituted means you should not write propyl, then you will get only mono-substituted compound. If you take ethyl and methyl, again you will get a di-substituted, which is incorrect in this question. Tri-substituted means we have to write only the isomers containing methyl groups. So let us take 3 methyl groups. So like this, 1 1 2, 1 1 3, 1 1 4. Don't think of writing methyl group here. After that, methyl groups 1 2 3, methyl groups 1 2 4, methyl groups 1 3 5. If you are getting any other structure, you just give the correct IUPAC name. You will realize that one of them is repeated. So if you shift it here, that becomes 1 2 4 only, same thing. So these are the possibilities I am getting: 1 2 3 4 5 6. 6 isomers. 6 isomers, that is in option B. So the answer must be B. Answer is B. So let us check the next question. In this question, he is asking how many cyclic Structural isomers are possible for C5H10. C5H10 degree of unsaturation is 1. He is asking cyclic isomers. So in case of cyclic isomers, we can take the possibilities cyclopentane, cyclobutane derivatives, cyclopropane derivatives. Whenever you are writing cyclobutane derivatives, here you are using 4 carbon atoms, 5 minus 1, therefore there must be one methyl group, In case of cyclopropane derivatives, totally there are 5 carbon atoms, 5 minus 3, remaining 2 carbon atoms, we can write either ethyl group or 2 methyl groups. So these are the possibilities. Let us write all isomers now. Cyclopentane only one possibility. Next one, methyl cyclobutane, that is also only one possibility. All 4 carbons of cyclobutane are identical. And in case of cyclopropane derivative, you can write either ethyl cyclopropane, otherwise dimethyl cyclopropane. In case of dimethyl cyclopropane, we can write methyl groups on same carbon, otherwise on adjacent carbons. So totally 1, 2, 3, 4, 5 isomers are possible. 5 is given in option B, therefore answer must be B. The given answer is B. And here in the question, molecule of C13H28 with the shortest possible parent carbon chain he is asking. Totally C13H28, in this formula degree of unsaturation is 0, and he is asking not the longest, he is asking shortest. Longest is obviously 13 carbon, shortest. So we need to verify the options. We need to start with 5 carbons. If 5 carbons is not possible, then we have to go for 6 carbons. First, let us try with the 5 carbons. So in that situation, 5 carbon chain I am taking 1, 2, 3, 4, 5. And my idea is out of 13 carbons, 5 carbons are present in the longest chain. Remaining 8 carbons must be present as substituents. Most importantly, whenever you are writing some substituent here, this side there is only one carbon. Therefore, here whatever the substituent you are writing, there must be only one carbon. Because if you write 2 carbons, what will happen? This will become the longest chain. So this is the last but one carbon. Therefore, here there is only one carbon. So this side also, if you have only one carbon, then it will be a 5 carbon chain. So here what I am doing, here I am writing the substituent. Here one carbon I am writing. Here one carbon I am writing. Here also one carbon I am writing. Even here I am writing one carbon. So let me prove, if you write another carbon like this, the longest chain will be like this, and that is not a 5 carbon chain, that is a 6 carbon chain. But first we have to write a 5 carbon chain. And here totally 5 carbons here plus 4, 9 carbons, 13 minus 9. So that will be remaining 4 carbons. Remaining 4 carbons I am writing like this, 2 carbons here and 2 carbons here. In that situation, you can see this is the longest carbon chain, 5 carbon chain. So this is the branch, here this is the branch. Even if you take like this, length of carbon chain is 5, but in this, without any hesitation, principal carbon chain is this one only, because this principal carbon chain has 1, 2, 3, 4, 5, 6. There are 6 branches. If you take longest chain like this, maybe this is giving same number of carbon atoms, but if you see the branches, 1, 2, 3 and 4, only 4 branches. If you can recollect the IUPAC rules, whenever 2 or more chains are possible with equal length, you need to select the chain in such a way that the chain with more number of branches. So this is the longest chain. So 5 carbon chain is possible. However, he is asking minimum. So the answer must be A. See, the given answer is A. And in the next question, the number of positional isomers possible for the compound including given isomer. So basically, how to approach this particular question, you just treat this compound as toluene derivatives. Toluene derivative, you are writing toluene derivatives, two NO2 groups. When you are saying this is toluene, this is the first carbon. So let us proceed like this. I am taking this one as a toluene ring, toluene molecule. In the given structure, NO2 groups are present at 1, 2 and 3 positions. Let me write 2 comma 3. Next again toluene I am writing 2 comma 4. Again I am writing toluene 2 comma 5. Again toluene 2 comma 6. Now why should I write at a 2 second position? You can write a 3 comma 4. Even we can write 3 comma 5. If you are trying for something else by keeping NO2 here, NO2 here, it becomes a second carbon, fifth carbon, 2 comma 5. 2 comma 5 means these two are identical. So these are the possibilities. Like this you have to solve the question. In all structures, you take a toluene ring like this, change the position of NO2 groups. You see NO2 groups are 2 and 3, 2 and 4, 2 and 5, 2 and 6. After that 3 and 4, 3 and 5. 3 and 6 does not exist because 3 and 6 and 2 and 5 they are identical. So the answer must be including given 1, 2, 3, 4, 5, 6. So answer must be C. So the given answer you can see that is C. Let us check the next question. In this question, they gave molecular formula of diphenyl methane. Structure was also given, and he is asking how many structural isomers are possible when one of the hydrogens is replaced by a chlorine atom. He is asking the total number of structural isomers possible when one of the hydrogens is replaced with chlorine atom. So for the sake of convenience, let me write all hydrogens and at what position they are present. Only one hydrogen atom should be replaced. This is the structure. What I am trying to convey, you replace either this hydrogen or this hydrogen, the result is the same. Result is the same. So here this hydrogen, the result is the same. You will get a one isomer. Now with respect to this carbon, with respect to this group, this is ortho, this is ortho, this is ortho, this is also ortho. That means those 4 hydrogens are identical. Those 4 hydrogens are identical. You replace either this or this, even this, including this. So you replace any one hydrogen of these 4, the result is the same because with respect to this group, this is ortho, this is ortho, this is also ortho. So that is the second possibility. And the next one, With respect to this is meta. With respect to this is also meta. With respect to this meta and meta, these meta hydrogens are similar. Meta hydrogens present at meta position. So here these hydrogens are similar, therefore that is giving a different compound. And last one, this is at a para position, this is also at a para position, those two are also similar, therefore this hydrogen or this hydrogen, the result is the same. So totally you are going to get a 4 different structural isomers, therefore answer must be A. Simply you replace any one hydrogen from this one, this one, this one, this one, same meta, this is meta, in fact this one, even this meta same, this is para. So ortho positions are 4, meta positions are 4, para positions 2, and this one totally 4 isomers you will get. This is A. Let us see the next question, and he is asking identify the relation between given pairs. So whether they are isomers or not, if they are isomers, what type of isomers they are. So here degree of unsaturation is 1, number of carbon atoms, oxygen atom same. So here this is aldehyde and this is ketone, therefore these are functional group isomers. First we need to check whether the molecular formula is same or not. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6 and 7. 7 carbons, degree of unsaturation is 1. So they 7 carbons, degree of unsaturation is 0. Therefore, they have same molecular formula. Basically, they differ in length of carbon chain. Therefore, they are chain isomers. And here we have 2 carbon atoms, 2 oxygen atoms, 0 degree of unsaturation in both of them. So they have same molecular formula. Position of OH group, here both the OH groups are on same carbon, here they are on adjacent carbon. Therefore, these are positional isomers. Next one, same degree of unsaturation, same number of halogens. So the molecular formula is the same, 1,2-dichloro, 1,3-dichloro. These are also positional isomers. And in the next example, 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, 4 carbons to 2 oxygens, and both of them are having same functional group, that is COOH. Most importantly, most of the students give the answer like positional isomers, but actually they are not positional isomers, because you see this is the longest chain and here this is the longest chain. So they are chain isomers, they are not positional isomers, they are chain isomers. And here 3 carbon atoms with alcohol, 3 carbon atoms with alcohol, position of alcohol group is different, therefore they are positional isomers. Next one, 1, 2, 3, 4 carbon atoms, 1, 2, 3, 4 carbon atoms, 1 oxygen atom, 1 degree of unsaturation, same molecular formula, one is ketone, another one is aldehyde, therefore they are functional group isomers. Next one, 1, 2, 3, 1, 2, 3, 4, number of carbon atoms are not same, there is difference of 1 CH2 group, they are not isomers, basically they are homologues. Next one, 1, 2, 3, 4, 1, 2, 3, 4, 4 carbon atoms, 1 nitrogen atom, same functional group. So length of carbon chain is different. Again here length of carbon chain is different. So 1, 2, 3, 4, 1, 2, 3. So these are chain isomers. Next one, same molecular formula. One side we have a propyl methyl. One has propyl and methyl groups. Another one has 2 ethyl groups. So they are satisfying the definition of metamers. And here again, if you see same molecular formula, here we have ether functional group. Here we have alcohol functional group. Therefore, they are functional group isomers.